right. Well, good morning, everybody. Happy Monday. Maybe not happy. Happy snow day, almost. Oh my gosh, I was clearing off my car yesterday, and that snow is the best, like heavy, dense, just wet but not slushy stuff to really compact, and like you can make a good snowman, make a good nice ice brick, snow forts. Oh my gosh, we should be outside building snow forts right now, in my opinion. But we've got some work to do before we can do that. Maybe this afternoon. We'll build snow forts in the afternoon. All right, oh, Michelle's here as well. Excellent. All right, so we really do have everybody. We've still got some trig to get through, okay? We're almost done. The end of the chapter is in sight. 2 more sections this week. And we can move on to bigger and better things. So today we are talking about inverse trigonometric functions, okay? And so basically with these, you take everything we've done so far and work backwards. Okay, it's a little facetious and seemingly ridiculous, but it's not that far from the truth. In fact, I would really say this is where the unit circle actually shines the best, is when you're doing the inverse. Because once you're given, some value, it's not as obvious maybe in your head, like, wait, where does that value go again? And so you might have more practice going forward. So maybe you have memorized, sine of 30 degrees, that's a half. Right? Sine of pi over 6, same thing, 1/2. But maybe given, inverse sine of a half, you're like, wait, which one is half again? You're not used to going in that direction. And so having a very nice reference chart, the unit circle, filled out, fleshed out for you to look at and visually say, there it is. Okay, it could be this one. Or, notice here, let's say I give you inverse sine of a half. Well, there's half over here on this side. Or there's another value that has the y for a half. And I don't have my laser pointer. You'll have to look over there, right? The 5 pi over 6. There's 2 different results there. That's kind of the downside to the inverse trig, is it's not as precise. And I put exact values here in quotes because for 2 very important reasons. One, we're still dealing with the exact values, as in we want the square root 3 over 2, we want the 5 pi over 6, right? We want those numbers. We don't want 0.3749, right? These infinite long decimals, okay? We're still dealing with rational expressions, even if we have the radical rational, okay? We want to keep the exact value format there. And part of it is just historical. Part of it is convenience from the unit circle and writing. And from a practical standpoint, the less rounding you do, the more precise your answer. So we always want to try to keep in an application style question, keep your answer in exact format until the last possible moment, to the very final calculation. Okay, we need to cut this beam, to be this long, this many, inches, 13 5/8 of an inch. And then you get out the tape measure and you mark it off and you make your cut. Okay. At that point, we'll need a more precise decimal or whole number, mixed number format, right? Something we can measure and make happen. But otherwise, keep it like this. And the other reason I put that in quotation marks is exactly as I said. There's this ambiguity with inverse sine of 1/2. The pi over 6? The 5 pi over 6? Is it negative 7 pi over 6, right? In theory, there's an infinite number, right? How many times does sine hit value of a half? Many, infinitely, right? Because it goes on forever. And so we have to contend with this switch in the domain and the range. So typically, let's just go with sine and cosine here. Okay, the domain used to be all the possible x values, right? It stretches out horizontally in both directions, infinitely, forever. So the domain is from negative infinity to positive infinity. And the range, default sine and cosine waves, their amplitude was always 1. So they would always have a range between -1 and +1, right? But now we've turned that around. Now we have inverse sine and inverse cosine. What's the domain and range there? We've got to reverse it, right? The domain is now from -1, +1, and the range is now, well, we can't actually switch. If we go on forever, if I take this sine wave and I let it repeat, vertically as much as I want, I fail the vertical line test and it's no longer a function. So we have limited ourselves to only one. I know this looks like almost like a tangent, okay, but it's not. It is, right, part of that way, right, part of the sine curve turned around, okay, and it would be going back the other way, but we've cut that off, so that's no good. We're going to stop here, and so we limit our range now to, in this case, negative pi to pi would be 1 whole cycle. Does that sound reasonable? Right? Let's think about this. This goes from one peak to another trough. Right? If that's continued, there we have a full cycle, so that'd be 2 pi. So we want a 1 pi gap. This goes from negative pi to 0 to positive pi. Nope, that's too far, right? Even that's too far. So we need our range to be down to negative pi over 2 to pi over 2, right? So this is negative pi over 2. This is positive pi over 2. This is positive 1. This is negative 1. Okay? That's, of course, applies to sine and cosine. Cosine then gets shifted slightly different, right? But that's the range we're dealing with now. Those are the allowed values, which changes things up significantly when we apply an inverse function to something outside of that. Right? We first have to convert. Wait a minute. What if you wanted the inverse sine of 5 pi over... Can you have inverse sine of pi over 6? That wouldn't even make any sense? No, it does not. Okay, before we go any further, let us establish this fact. In fact, I'm going to stick it off to the side here. Okay? Trig functions always go from angle to a side length, right? And I say side length because I'm talking about we're establishing a little right triangle here. So we go from the angle to some side length, right? Okay. Inverse trig is the opposite. It always takes a side length and outputs an angle. This is going to be very important when we get to the composition of functions, because we have to know what to expect where. Where will we see angle type values? Where will we see side length type values? Okay. Angles, if given in degrees, great. Those are easy and recognizable. That you see the little degree symbol in the corner, it's a dead giveaway. Radian angle measures a little more subtle. If there's a pi, that's a dead giveaway, right? If you see a pi, dead giveaway. Okay, so we've got the degree sign. We have pi as a dead giveaway. Okay. You could still have other fractions, possibly. Somebody could ask for the inverse sign of 1 radian. Okay. But 1 radian isn't on our unit circle, so we don't really have to concern ourselves with that, right? Look back at your unit circle. Okay, notice all of the radian measures, except for 0, involve pi. Okay? So that limits things a little bit. What else do we have to deal with? Well, on the one hand, just going backwards is simple enough. Okay? Here's this one, work backwards. You either know it, or you know your unit circle and you can look it up, or you have some other table of values you can look it up. A calculator, again, is not going to give you the exact value, so that's not a reliable source. Whoops. Any questions on those basics so far? No? All right. Then let's get into composite functions, because this is going to be the most difficult, right? This is where you have function of a function, okay? F of g of x. That's composite functions. The input of one function is the output of another function, okay? So first, find g of x, okay? Then input 1 into the other function f. In this case, we're dealing with trig functions, so and inverse trig functions, so often we'll find function of inverse of something, right? Or f inverse of f of x. And usually, these undo each other, right? That's a really handy feature, right? Sine of inverse sine of x gets us back to x, right? It's literally perform an operation and then perform the opposite operation, right? Go backwards. Well, we're back to where we started. Except for this. Except that limit on the range is going to throw us off, because not every possible x is going to get perfectly reversed. Okay. And I bring you to this lovely table here on the book, making the same point. The inverse properties. Okay. If I take sine inverse of x and then take sine of that, yes, I will get back to x. If x is between -1 and +1. Okay? Because if it's beyond that, then it was outside the domain of one of these functions first, and it doesn't work. It doesn't automatically give me this, right? I have looped back around my unit circle. Okay? Think about if I asked for, again, inverse sine of 1/2. Well, which angles give me 1/2? It could be pi over 6, could be 5 pi over 6. Okay? Only one of those is defined on the function, right? And similarly, right, if I go the other way, what is sine inverse of sine of x? Well, usually they will undo each other perfectly. Sine of 30 degrees is 1/2, inverse sine of 1/2 is 30 degrees, back there, right? So long as, right, I gave you the 30-degree version, or the pi over 6 version, not the 5 pi over 6 version. If I give you 5 pi over 6, sine of 5 pi over 6 is 1/2. Okay, let's try that. Okay. Sine of 5 pi over 6 is 1/2. But sine inverse of 1/2 is not 5 pi over 6. It's going to give me pi over 6, because this will always return the answer within its range. Okay? It will give me the closest to 0 possible answer. Has to be within this interval in order for you to get the exact same thing back out. See the difference there? So if this is not in your notes, add that section now. This is going to be very important because that serves as a quick check. You're going to look at things and be like, ooh, look, these operations undo each other automatically. It's just x. Wait a minute, red flag, hold on. Is it on the appropriate range? Let me check, okay? So it has to be in the range of, in this case, the range of the outer function. Okay? So the range of sine is -1 to +1. I better make sure my x comes -1 to +1. Because the range of the outer function has to be the domain of the inner function, right? It's got to be within the domain in order for you to have a valid function operation there. Questions there so far? All right, then let's do a few more examples. Let's switch back to here. Let's try this one, right? Evaluate cosine inverse of cosine of 9 pi over 4. Hey, cosine, inverse cosine, those undo each other. Is it just? That's a terrible pi. 9 pi over 4? What do you think, yes or no? Well, the teacher's asking about it, so it can't possibly be the easy one, right? So the most complicated results would be no. It's not just that, right? That'd be too easy. So I'm going to go with no. You'd be right. No. It doesn't work. And we can check, hey, what is the range on cosine and inverse cosine? Well, cosine has the range -1 to +1. Inverse cosine, to get one non-overlapping loop, goes from 0 to pi. 9 pi over 4. 9 is more than 4, right? So this is more than 1 whole pi. Like, I don't even need to know any more than that. 9/4 is more than 1. It's more than a pi. Doesn't work. It doesn't automatically give us the right answer. So we got to go the long way. Ah, geez. The long way is just do 2 trig operations, okay? Big deal. Find, first, we're going to find cosine of 9 pi over 4. All right, hey, pi over 4. Those are the 1/8 bit, right? Here is 0, here's pi over 2, here's pi over 4. It's the 1/8. I need 9 of those, so 1, 2, 3, 4, 5, 6, 7, 8 all the way around. 9 back where I started. Oh, cosine of 9 pi over 4 is the same as cosine of pi over 4. Okay, ooh, what else do we remember from our unit circle? If you have to look it up, look it up. I'm going to try without. We'll see how well I do. I know that there are only 3 critical numbers on there. One of them is square root 3 over 2, one of them is 1/2, and one of them is root 2 over 2. Pi over 4, that's that 1/8. That's the guy in the middle. He's the nice perfect symmetric one. He gets the most symmetric answer, which is the 2 over 2. So it doesn't matter. It's cosine or sine. It's always going to be the same thing. It's either square root 2 over 2 or square root 2 over 2. So cosine of pi over 4 should be square root 2 over 2. How did I do? There it is, pi over 4. Cosine gives me the horizontal, the x value, which is square root 2 over 2. Whew. Okay, not bad. And now we'll take that and plug it in to the outside function. So now we find cosine inverse of square root 2 over 2. Okay? What angle between 0 and pi has an x value of root 2 over 2, right? Has a cosine of root 2 over 2. We just found it. We just did it. It was that equivalent angle, right? It's going to, should be our pi over 4 is the best, smallest angle in the range. They will give us a cosine of square root 2 over 2. Okay? It was only not the easy mode because it wasn't the exact same as 9 pi over 4. It lands on, they are coterminal angles, right? That's very useful. Your coterminal angles will help you here. Let's do another one. Let's do secant of inverse tangent of negative 4 over 7. Give an exact value. Negative 4 over 7. Mr. Apple, where the heck is negative 4 over 7 on the unit circle? I memorized my unit circle pretty good. There's no negative 4 over 7. There is no over 7s on this unit circle. There wasn't even a pi in that, right? Hold the phone. Hold the phone. Is it supposed to be an angle? Am I expecting an angle argument here? I've got inverse on the inside. Remember, inverse takes a side length and then gives an angle. Oh, okay. We're not expecting negative, it's not negative 4 over 7 radians, okay? That's one of the lengths, one of the sides. Or in this case, tangent is the ratio of the two sides. Okay, Mr. Apple, but still, 4/7? Where the heck is that? Do you see any combination of these angles here where I'm going to end up with 4/7 if I divide one of these by the other? I don't see it. What are we going to do? The unit circle has failed us. This is not on the unit circle. We can't rely on it. So, instead, we're going to have to think through this and build our own angle, right? Let's imagine some angle somewhere creates a right triangle, some angle theta that we're looking for, okay? And that angle creates some opposite side, right? Some adjacent side. And our hypotenuse here is always 1. And the tangent, right? The tangent of that angle theta would be the opposite over adjacent. We remember our SOHCAHTOA, okay? Which means the inverse tangent of that opposite over adjacent will give us back our angle theta, right? Okay, okay. See what I'm doing here? Now, that opposite over adjacent we know is given right here. Inverse tangent of what? Of the opposite over adjacent. Whatever the opposite over adjacent are, they will reduce to the fraction of -4/7. You with me? So can we just say that this is call the opposite -4 and the adjacent 7? Whether or not that's actually the measurements, I don't care. Okay? They will work. Okay? And yes, this is -4, which means it's actually going down, so I should redraw my triangle to come like over and down from here. But doesn't matter, right? It doesn't make a difference. But we can treat this as if these were the opposite and the adjacent sides of -4 and 7. I still don't actually get a value for theta. I don't need a value for theta. What would be, pretend that I did. If I did, secant of theta would be, remember your expanded trig functions, secant starts with s, so it is not sine. They always do that to you, right? They reversed it. Secant is not sine. It would be nice if it did. Okay, so if it's not sine, it must be cosine. Secant is the inverse one, or not inverse, reciprocal, sorry. 1 over cosine of theta, right? And cosine of theta, remember your SOHCAHTOA, so cosine is adjacent over hypotenuse. Which means secant is flip that, so it would be hypotenuse over adjacent. I don't care what the theta is. I don't need to know what the angle is, because whatever that angle is, it's this angle right here. It's this one that fits in this triangle of 1, 7, -4. From that angle, I just need the hypotenuse, which is 1, because we're on the unit circle, and the adjacent side is 7. I should get 1/7. Do I get 1/7? Okay. So there is our answer. So, unit circle, awesome tool, handy shortcut. Okay? When in doubt, go back to right triangle trig. Build a triangle, okay? Because all of these functions are some relationship of two sides of that triangle. Anything they give you will give you enough information. I can work out some value for each side that can appropriately be used on the other side. Okay? This is not 1, by the way. I'm looking at this and I'm realizing, wait a minute. I said unit circle. But is this really a unit circle? Can you have a hypotenuse of 1 if the sides are actually -4 and 7? No. Can't do that, Mr. Apple. Nobody called me out on it. It's not 1/7, darn it. All right. We gotta be thorough. Let's be correct here. Let's fix our mistake. We assume too much. We can at least do this much. What is the hypotenuse there? Well, here's where good old Pythagorean theorem comes in. Okay, so this hypotenuse is going to be a squared plus b squared equals c squared, so it's the square root of 4 squared, that's 16, plus 7 squared, that's 49. So this is the square root of 65. Square root of 65 is something more than 8. little bit. Leave it in exact form, right? It said exact form, leave it as exact form. H is squared is 65. All right, so it wasn't 1. Oh, no, sorry, leave that as H. Square root of 65 over 7. There we go. That's better. Okay, do you feel a little bit better about that? Like I can hear you nagging at me. Mr. Apple, I think you missed something there. That's what I missed. The hypotenuse. Build a triangle. Pythagorean theorem. Find all the sides. Assemble new ratio of sides. Right? That's all it is. So this last one here, same deal. Even if they don't actually define it for us, we can still use that trick. Okay? Use a right triangle defined, in this case, cosine of sine inverse of 2 over x in terms of x. Ooh, okay, so we're going to leave it as a variable. And we're going to assume that x is positive and that the trig function is in fact defined, right? We could come up with something and stick it in here, several million there, and it would screw this up, and then it wouldn't be defined because it wouldn't fit in the domain of the function, right? So let's assume it works. Okay, so build your right triangle. They gave it to us in the directions. Use a right triangle. Okay, build a right triangle. There we go. Let's pick this one, call it theta. Why? Because I like it. You don't have to use theta. You can use something else. Do you like a different letter? Let's use a different letter. Alpha, just to be different, okay? Theta is most common, don't have to. I know that sine inverse of 2 over x. Okay, so sine of alpha, so it would be opposite over hypotenuse. And in this case, they're telling us it should be 2 over x, right? See that? We're just going to take that ratio from sine. If you're taking the inverse sine, that is my sine ratio. Okay, so the opposite side should be 2, and the hypotenuse should be x. Find the third side. No, go away, keyboard. Not typing here. Find the third side. Okay, so call that b. b is equal to the square root of hypotenuse squared minus other side squared. 2 squared is 4. That's it. That's what b is. I don't know what x is, so this is the best I can do. Okay, and then which one do I actually want to find? I want to find cosine. Okay, so the cosine of alpha, so katoa adjacent over hypotenuse. So it's going to be the adjacent side, that b that we found, so square root x squared minus 4, over the hypotenuse x. That's a simplified fraction expression in terms of x. That's it. That's our answer. I can check with my answer from ahead of time. Yep, there it is, right? There we've got it. Oh, that's really convenient. Good job, right triangles? Okay, remaining questions on these types of problems. Exercises. I hope they're exercises. They shouldn't be problems anymore. No? All right, then your homework is as posted. Did get posted, right? Yeah, those use exercises. Okay, 1 through 45 odd, plus the vocabulary ones, of course. Not be too terrible. Most of them are fairly shorter and of the simpler format. Okay, but go through, practice that. And you've got 10 minutes to go ahead and get started, okay? if you run into a question at that point. So I recommend, again, whenever you've got extra time to start homework in class, don't start on the first problem and go one at a time. Look over the whole thing, read through it, try to find, ooh, that one looks the toughest. Ooh, this one looks nothing like the example he did in class. Mr. Apple, can you explain how this one works? Because it looks completely different. I don't see the connection there. Okay, that's what you should be looking for right now. Do that. Ask questions. But otherwise, I'm going to stop the YouTube stream here.